Determination of role and friction force on a plane elastic surface. Article 9.4 of the book Mechanical Systems, Calculations of the Marine Facilities. A little bit about the theory of the resistance to the rolling, the resistance of friction to the rolling. If we have, for example, the roll in the elastic surface, so when we roll this mechanical body, this roll, when we move this roll will experience the resistance to the rolling, and subject is how to find the moment of the rolling turn. So let's consider the roll shown on the figure 9 for 1A. The roll is under the action of the force. At least this is the force of the roll weight, the roll characterized by the radius r, and the point 0 we can associate with the reference point of the coordinate system, and we have the force, tangential force Q applied rightward to the point 0 level, and this roll experiences the friction. The friction is not definitely like the dry friction, the sliding friction. This is the resistance to the rolling. And in the state of the rest, we have the balance of the forces. The force of the wedge is in the balance with the force of the reaction of the support, elastic support, supporting the point C. So we have to consider as well the magnitude of the moment which turns this roll. So of the roller with the moment equal to minus q minus q by the r. R is the radius of the roll. When reacting a certain limit value of this force, the roller begins to move. The conditions of stationary balance of the roller on the surface, we can consider if we just assume a definite elasticity of the support. If the support is not elastic, so we have zero resistance to the rolling motion of the roller. But if we have the deformation of the surface, due to the rotation of the roll when rolling, rotation of the roller when roll, the point of the application of the support reaction N moves to the direction of the rolling of the roller. So it moves for definite magnitude as arm H. We have the friction force applied in the same point C. This is the point of the support when the roll is rolling. So the balance equations we will have when the roller roll. The balance equations are the total of all forces projections on the abscissa axis have to be equal to 0. The total of the forces on the ordinate axis is equal to 0. Then from the second equation we have that the reaction of the support equal to pi p the force, and the force of the moving the transverse force Q applied to the point 0 is moving have to be with the friction force, the force of the resistance of the roller rolling, the balance have to be equal to 0, and the moments of the rotation of the, for example, around the point C, point of the support, could be another one point, but we can take the C, have to be that the around the point C, that the pi, the weight of this definite one roller by HH is the arm rising due to the deformation of the support. Perhaps this elastic deformation after the movement, the shape, the flat shape of the support restores, but it is in the after. But when it rolls, we have the displacement of the point of the application of the force to the direction of it moving the H. And we have the transverse force Q multiplied by RR is arm of this force rotating around the point C of the wheel or roller or around the point C. So we can find here that due to the other balance equations that the arm is equal, arm of the force of the friction equal to to find the force of friction, the arm of the action of the weight of this wheel when it moves on the elastic surface will be H equal to QR is the moment rotating due to this third balance equation, the equality to zero of the moments equal, and divided by P. So this is the H. And when H can be maximal, with the maximal magnitude, where the delta, we denote the maximal magnitude of the arm of the displacement of the point of the application of the reaction of the support, that is a maximal arm of the moment between the force of the wedge and the force of the support reaction, maximal arm. We can denote this like a delta. The coefficients of rolling friction, the rolling resistance. So the total of the moment, the sum of moments of forces relative to the point C of the rolling rotation. This total of the moments have to equal to zero. It's a balance equation. The condition of the stationary balance of the roll has the form that the arm, actual magnitude variable arm, have to be less than delta. This is a condition of the stationary balance. Delta is coefficient of the rolling friction. It is equal to the maximal magnitude of the H of the arm between the force of the wedge and the force of the support when the forces are shifted due to deformation of the support plane, or maybe deformation of the wheel itself, as a result of the elasticity of the material of the support plane, and maybe the elasticity of the material of the wheel of the roller. The moment of rolling friction, the rolling resistance is equal, or resistance of friction is equal, that is moment equal to delta, the maximal magnitude of the arm of the forces, delta, the same time the coefficient of the rolling friction multiplied by the support reaction. If only the support reaction is for the wheel under the own wedge, and could be equal to P, but sometimes we have another external forces, so the support reaction N could be other than the wedge of the wheel. In terms of the moment of rolling friction and the action forces, the force Q, the transverse force here, Q, bringing the roller out of state of motionless equilibrium, and the force N, pressing the roller to the supporting surface. Conditional stationary forces of the roller has the form, the moment of the friction moment, the moment of the resistance of the rolling equal to, have to be less. This is the condition of the staying of this roller, and the rest have to be less than delta multiplied by N. And or Q have to be less, transverse force have to be less than delta. Delta is a coefficient of the maximal arm of the shifting of the forces, and the action of the support force and the weight or other external forces, vertical component onto the roller, the maximal magnitude of the arm, which is the consequence of the deformation of the material of the support and the roller H, and the maximal magnitude equal to delta. Delta at the same time is a coefficient. Coefficient we have to multiply arm, and the coefficient multiplied to the force to have the moment of the resistance. Then the transverse force have to be in the proportion of the arm of the application of this force, R, the arm of the application, the radius for definite one wheel. And the delta is the displacement of the point of the application of the force due to the deformation of the support and the wheel. So exercise. To the uniform roller, we have uniform roller with the same radius, all radius, shown on the figure 9.4.2, weighing 2 kilonewton. The horizontal force applied. Horizontal force applied here, they assign the rolling friction coefficient. This is a maximal magnitude of the arm of the forces, weight, and the support reaction when the roll, when the wheel moves. The sliding friction coefficient as well applied. 0.2 could be any kind of the metal, maybe carbon, steel. They're very big, but could be any kind of the metal. sliding friction coefficient, the roller radius 0.6, R is 0.6, and the size 0A, this is size between the center, the axis of the wheel and the line of the application of the horizontal force F is equal 0.4 meter. The elevation of the point of the application of the force above the roller axis. The conditions of balance, first we have to consider the conditions, all projectile forces on the abscissa axis equal to 0, then we can find that the force transverse have to be equal to the force of the resistance of the rolling, or maybe friction as well. So because this phenomena, not only the deformation of the support, the support plane and the wheel support deformation causing the raising the arm between the points of the application of the support direction and the wedge, causing the resistance to the rolling. It could be as well the friction, the dry friction due to the roughness of the surface. And the second is total of the components of all forces on projections on the ordinate axis y have to be equal to 0. Then we have only two forces, the support direction and the wedge have to be equal to 0 in the total. But with the other signs, because we forces have other directions. Well, the total moments relative to turning point D of the roller are total of the moments. Total moments have to be equal to 0. We consider the point D as for the consideration of the balance of the all moments acting onto the rolling wheel. This is P, force P by delta. It could be the force N as well, but we have force P and force N, not so much importance. They are of the same magnitude. P by H minus Q by R. Q by R, this is the friction force Q. This is have to be equal to Q, and the N equal to pi. So, excuse me, here is bit we have to improve this. Have to be the force. The another one, summand of the rotating moment have to be the force transverse F, and instead of R we will have the R as well as radius and the elevation between the axis of the wheel to the point of the line of action of the force F. Okay, we have to improve to that. This is an error in the description of this one balance equation. Sliding of the roller can occur when the action of the roller on the force is greater than the force F1 equal to the friction force. Then the sliding friction, dry friction factor we assigned to 0.2, and the wedge equal to the force 0.2 multiplied by 2 equal to 0.4 kilonewton. Rolling can occur under the condition that the roller is acted upon by the force which is greater than, and delta is we assigned as well. Delta is 0.006 meter delta. They have the dimension of the delta because physical sense of delta is the arm of the application of the force. And the F2 have to be, after the substitute of the PP, the wedge equal to the support reaction force, and the AD is the total of the radius and the elevation of the line of action of the force over the axis of the wheel. Together we have AD, the radius assigned is radius assigned 0.6, elevation 0.4, so we have 1 meter. DA is 1 meter. DA, yes. Let's look please here that actually we consider the correct description of the balance of the moments here, because we consider not the radius of the application of the definite force Q, but we consider the AD of the application of the point P of the point AD, the arm of the point F2. F1 and F1, just because we consider the dry friction phenomena here, we consider the roller resistance phenomena. So we have F1, F2, we have to make a choice. What is the minimal one of them? F2, we have to substitute data of delta, arm, maximal arm of the action of the due to the deformation of the support, and the wheel could be restored. And the next, the shapes of the support and the wheel is elastic deformation. But anyway, in the process of the rolling, we have the arm, the shift of the application of the point N and the point P. So this is 0.006 divided by 1 AD, 1 meter multiplied by 2. 2 is the pi, P is 2 kilonewton, the horizontal force applied. So next we have 0.012 kilonewton. So conclusion, we have the sliding and rolling the roller is absent when this force is no more than 0.012. So if it will be more than 0.012, the wheel will roll, and if the force will be more than 0.4 kilonewton, the wheel will roll, and besides it will slide. It will slide. I mean, dry sliding will be if the force will be more than 0.4, but the minimal is 0.12 kilonewton. Next exercise, we will have for this definite one scheme of figure 942b of the force application, force F and angle of the 30 degrees. So this force increases the support reaction as well, not only the weight, but the vertical component F multiplied by the sine of the angle of the 30 degrees will be the vertical component of the force F, and the horizontal by the cosine of this angle. But let's consider for the second exercise the data. Exercise 2 to the uniform roller, all about the same, but another one, yeah. This roller weighs 700 newtons, about a little bit less than 70 kilos mass. The force F applied at angle of 30 degrees, the radius of the roller is 1 meter, the sliding and rolling friction coefficients are the friction coefficient, sliding coefficient just for the dry friction is 0.2, and rolling resistance factor is 0.00 meter. Conditions for motionless equilibrium of the roller on the surface. In the prerequisites onto the in the projections on the axis of the coordinate system, flat coordinate system 0, x, y are the total of the forces is equal to 0. Then the total forces on the abscissa axis we have F and the friction force. F by the cosine of 30 degrees with the minus sign, with the plus degree, because we have the x directed leftward, and what you have, and the friction force, yes, we have as well, and the resists it is for the roller on the surface. And the total of the projections of the forces on ordinate axis is quite equal to 0. That is the support direction we directed upward, and minus pi p is the weight of the vertical projection of the external force inclined, as well as the total of the moments of the relative from the point of rotation C of roller is the total of the moments has to be equal to 0. So this is support reaction about the coefficient of the rolling resistance equal with the physical sense of the maximal arm of this force action when the wheel rolls over the elastic surface. So, and the wheel of the elastic material could be, and the force of the assigned external force as well have the horizontal component by the cosine 30 degrees and multiplied by the 0c is the angle, excuse me, this is OC, the arm of the rotation, yes, this rotates, this is the total of the moments around the point C. Around the point C. Okay. And this could be the friction force too. Yeah, with the okay, at OC equal to R. Sliding of the roller will occur when the roller is subjected to the force greater than the friction force is greater than the friction force factor multiplied by direction. The direction consists of two components, P and the external P at the weight of the roller, and the external force with the sine of 30 degrees factor inclined external force. And the force is applied at angle of 30 degrees not only raises the pressure of the roller on supporting surface, but also affects the roller in the direction of the overcoming the force of friction, which condition the balance of roller would be no less than the friction force have to be in which condition balance of roller would be equal. The friction force equal to the force by horizontal component by the cosine 30 degrees of the inclined force. Then the conditions of balance at which the roller will not slide has the form. The force by the cosine have to be less than the friction coefficient, and this is a total vertical reaction which you multiplied by the friction coefficient to find the friction force. And the applied force would be no greater than for the staying of the wheel in the rest, but be less than, considering this condition of the staying the roller in the rest, which is the criterion that the friction coefficient by the P is this is a force, and this subject to find F, the force external force F. We have, after the mathematical transform, find in the numerator F by the wedge of the wheel divided by the, after the mathematical transform, by the cosine 30 degrees minus F factor of the friction by the sine 30 degrees. So we have as the 183 Newton. This is minimal force which we have to apply to the in the direction of the force F, minimal magnitude of the force F, which can cause the sliding of the roller sliding. So next we will consider the rolling. The rolling will occur if this one force as F by cosine 30 degrees multiplied by the arm. Arm is the radius of the wheel have to be more than the rolling resistance, the same, the magnitude of the support direction vertical, and the product by the delta. Delta is the coefficient of the resistance for the rolling, depending on the material and geometry of the surface, and the rolling wheel material as well, the geometry radius of the rolling wheel, and this is arises definite arm of the shift of the points of the application of the support reaction and the wedge, the forces. They will not be on the same vertical when the wheel of the elastic properties and the surface of the elastic properties of plastic maybe don't know so much important to the consideration of the roller if they moves, if the wheel rolls over the support. So we have this delta assigned as well, 0.08. And we can derive from here the second magnitude of the force we have to apply to move the wheel. This force have to be more than this is what is no more than 183. The force have to be no more because we assume what is the force which do not exceeds the force of the drive friction resistance. So this is a force what we have applied to force the wheel to roll. The minimal magnitude of the force applied at the angle of 30 degrees at which the roller begins to roll with sliding. So this will roll and slide. This is a force enough for the sliding, for the with the drive friction, and with the rolling this enough too, because this is more than 6.5. So the minimal force is 183 Newton. This is the answer for the issue. The issue we had what have been the force magnitude to cause the rolling and sliding of this definite one wheel together. This could be the subject of the research of the the braking of the motion of the any kind of the car, maybe the I don't know, maybe if you consider the conditions of the braking, for example, the railway car. In this definite one case, it could be like to find what is the force which can cause the rolling and sliding this car together if it breaks by the railway, for example, if it moves by the railway with in the process of the slowing down under the action of the brakes of the roller. Questions and comments. The crumple off section of surface of the roller and the complete and the crumple off section of the supporting surface, which in case of the occurrence of rolling friction force. If we have the absolutely solid surface and absolutely solid wheel, this wheel and the surface do not cause the resistance for the rolling over the surface of the roll. It's only the subject of the local deformation of the point of the contact of the wheel and the surface. The deformation could be the restorable or not restorable deformation. Not so much important when you consider the rolling. The deformation cause for the resistance to the rolling. The state of the motionless balance of the roller in explicable based on the model of an absolutely rigid body, the roller or the supporting surface. In the state of motion balance, only zero force can cause the it can cause a balance. Absolutely zero force in the balance of the on the wheel on the absolutely rigid body, absolutely solid wheel. The force which any force more than zero have to roll this wheel over the surface. And this force have to be zero to keep it in the balance. 9.4.2, the conditional motionless balance of roller in the form of limiting displacement of the line of action of the reaction normal to support surface on the projection of the axis of the roller onto the support surface when this surface and the roller, the two are deformed by pressure force to the normal support reaction. The motionless balance of roller in the form is if the force not enough to cause the rotating moment of the wheel, which would be more than the weight of the wheel multiplied by the arm rising due to the deformation of the wheel and the supporting surface. The force have to be applied, external force have to be greater, transverse force greater to overcome the balance. If the force is less, then the product of the weight or with total of the other vertical components of the external force multiplied together onto the delta, the factor of the resistance for the rolling, dependent on the material and geometry of the support surface and the geometry sizes, radius of the roller with the definite, considering the definite material of the roller. If this force is not enough to apply the definite arm transverse force, the wheel will be in the balance with no moving. 9.4.3, dependence of the rolling friction moment on the rolling friction coefficient, which depends on the rigidity of the supporting surfaces and the rigidity of the roller and on normal support reaction. The rolling friction moment is proportional to rolling friction coefficient, and the force or the vertical force of the support usually equal to the total of the weight of the roller together with the vertical components of all forces, external force applied to the roller. 9.4.4, the sequence of assessing the stationary equilibrium of a roller taking into account the conditions of its rolling and sliding. We have to consider the the conditions of the balance of the forces, projections on the axis and coordinate axis, the balance of the moments. For the flat state, the moment is scalar magnitude. So, considering this, we can find the magnitude of the external forces, which is enough or not enough to cause the dry friction with the sliding of the roll of the wheel and of the roller, and we can find the force which is enough or not enough to cause the rotation of the roller, considering the coefficient and the weight of the roller with the definite factor of the resistance to the roller rotation proportional to the maximal arm of the shifting of two forces, parallel forces of the vertical component of all forces with the weight acting on the roller on one hand, and the vertical component of the support reaction on another one hand, when they are not on the same line. So when the line shifted, the points of the application due to the deformation of the support surface and the deformation of the wheel, they can cause the resistance. And the sequence is to find what is the magnitude of the force, which can cause the dry sliding, and what is magnitude of the force which can cause the rolling. And the conclusion is what is assured is, if assured, to find the conditions of the balance in the rest of the roller on the surface, or what is the condition of the movement of the roller begin as to slide and to roll. So next we will have two magnitudes of two forces due to the dry friction and due to the rolling, the required forces. And next to do the conclusions, which one of two forces we have to choose as the assigned magnitude to find. Thank you.